Hi, I'm Martha. This is joint work with Dea Bankova, who was an MSc student at Oxford last year, Bob and Dan. Thanks to the organisers for accepting the talk, and thanks to you all for making it through to the last talk. Manoush and Dan have both given a really good introduction to what compositional distributional semantics is, so I won't go through that in too much detail. But the question that this research wants to answer is how we can start to incorporate logic in compositional distributional semantics, because vector spaces in general don't have a natural logical structure. So in order to do that, we use mixed states, or more generally positive operators, to represent words. Positive operators have the learner ordering where A is less than B if B minus A is positive. And we use this ordering to represent entailment, and we also introduce a graded version which is useful for linguistic phenomena. So for example, you can have dog roughly entails pet, because quite a lot of dogs are pets, but there are other dogs that aren't pets. And we show that this graded entailment lifts compositionally to sentence level. So this work is also similar to some work that Manoush, Dimitri Katsaklis and Esma Balkir have also done. So there's various things that you can look at around here. So yeah, as we know, compositional distributional semantics has this general program for mapping some chosen syntactic structure, which is your grammar, to a semantic framework. And we need the syntactic category and the semantic category to be closed. So here we've got, this is on the left-hand side, we've got the syntax, which is pre-group grammar, and we've mapped this over to the semantics. And really the grammar, you can think of the meanings of the words are here, and the grammar is the cups and caps, the morphemes that we're applying. So how can we represent words as positive operators? Well, so we've got density matrices as convex combinations of projectors. And then we can think about words or concepts in general as being collections of items. So for example, pet will have dog, cat, tarantula, and then these probabilities here are going to be higher for dog and cat than they are for tarantula. And then we've got various, if we want to lift these density matrices to other positive operators, there's various choices for normalization. So if we stick with just trace 1 density matrices, then that doesn't work very well with the learner ordering, because no words actually compare with each other. What we can do is to divide through by the maximum eigenvalue. That maps each of the matrices to another positive operator. Their different words do compare, and what's quite nice about that normalization is that we get projectors coming out. So the maximally mixed state goes to the identity, and then on each of the subspaces that goes to projectors on each of the subspaces. Positive operators form a compact closed category with completely positive maps, and so that category, CPM F Hill, has the same graphical characters as F Hill but with thick wires. So we've got cups, caps, tensor products, for example. And so this is exactly the same as what Manoush said, really, but so we assign the semantics by a strong language functor. We've got a string of words here with grammatical types in the pre-group grammar, which reduce down to a sentence. So this string of words is a sentence. If this semantics brackets WI is a positive operator representing this word, then the meaning of the full sentence is the grammatical structure applied to the tensor product of those positive operators. And it kind of looks like this. This is where you've unfolded it. So we want to think about a general setting for approximate entailment. We can build an entailment preorder on any A plus D equals B. So if A and B are positive operators, this is basically saying what the learner probably says. We then introduce an error term, E, and add that into B, and that's just adding the sort of amount of stuff we need to add in to let A entail B. We restrict attention to certain errors in a complete neat semi-lattice and take the lower bound in E, and then we can also assign sizes to those errors. So in particular, if A and B are positive operators, we take the lattice to be all operators of the form 1 minus KA, which is ordered by the size of 1 minus K. And then we take K to be the strength of the entailment, and we call that K hyponymy. So hyponymy is basically the is-a relation. So you've got a dog is a mammal. So the dog is a hyponymic mammal. So A is a hyponym of B if B minus KA is positive. That's just a rewriting of what was on the previous slide. And we're interested in the maximum of such K. And we can work out what that is. I won't go through that, but it's possible to just calculate that. The properties of K hyponymy are that it's reflexive when K equals 1. So this makes sense because a dog is a dog. It's anti-symmetric when K equals 1, but neither when it's less than 1. It satisfies aversion of transitivity, and it's continuous. So when we change A slightly, there's a correspondingly small change in the value of K. So we want this notion of entailment to work at the sentence level, and because we do actually map all our sentences down into one space, you can actually compare any two sentences just directly by forming a positive operator for that sentence. But if, in fact, the sentences have similar structure, we can also look at the extent of the entailment between two sentences based on the behaviour of the words within the sentences. So, for example, if we've got dog is a K hyponym of pet, and park is a K hyponym of field, then how are these sentences going to be related? Well, what we find is that, in fact, the product of those graded entailment values provide a lower bound on the extent to which two sentences, one sentence entails it. So in summary, we've got a graded measure of entailment between any two words in this compositional distributional semantic framework. We've shown how the maximum entailment between two words can be calculated. This applies to any pair of sentences at the sentence level, and it also interacts really nicely with compositionality. So in further work, we need to think really about what we're going to do for normalisation. So there's a master's student who's been looking at this, and it seems like this maximum eigenvalue normalisation has actually got some quite nice properties. We need to look more at introducing other logical connectives, how we can apply this to non-identical sentence structures, and the sort of crowning glory of this will be to implement a full dynamic epistemic logic within this, so that then we can incorporate dynamic epistemic logic and compositional distributional semantics. So I've just got one more slide, which is, if you like this and the previous two talks, you'll love tomorrow's workshop. We can take registration on the door. It's £10, and it starts tomorrow at 9:30. Thank you.
Questions?
I think you mentioned it, but I went a bit fast. What kind of structure does this entailment order have? The words?
We have CPM of FL, so...
No, I meant, is it a lattice?
It basically gives you a partial order, but it doesn't form a lattice, which is a shame.
So how are you getting the logical connectivity?
don't know yet.
Did you consider what to do with antonyms?
Yeah, so with the sentences with identical structure, you do need them to be upwardly monotone, so it does include antonyms and words like not, and so I think that will come into how we deal with the logical properties. I mean, so with two antonyms, there should be some relation between them that reflects some kind of
Complementation.
something like that, yeah. So yeah. So yeah, some sort of they'll be in ortho-complemented subspaces, but then I guess they won't quite be. It's not as simple as just plain subspaces.
Any other questions? So, if not, thank you.